once in a while, we have the opportunity to introduce an old friend. And also every once in a while, we have the opportunity to have as a guest a world-class scientist. And this particular time, we get to do both. Because I've had a friend for more than 20 years by the name of Barry Setterfield. And he became very famous many decades ago as he with Trevor Norman together predicted, or understood, I should say, that the speed of light has actually been slowing down. And they were greeted by a lot of guffaws from the physics community. In fact, I had two of my oldest friends that were very prominent in the physics world take me to dinner to try to give me guidance not to get caught up in this crazy idea that the speed of light was not a constant. And they took me to a nice dinner, and I listened politely, but I privately resolved to ignore that. And I chose to side my remarks in the direction of supporting Barry Setterfield and Trevor Norman's disclosure the speed of light has been slowing down. It was many years later that it became widely understood and acknowledged that they were right. And so Barry Setterfield is a very familiar name to people in the physics world and certainly in the Christian world as just a first-class guy that's committed to the Lord Jesus Christ. Well, a monograph landed on my desk a few months ago, and it was on my desk less than a week or so when I realized I needed to repair a delinquency and track Barry down. And so I arranged to stop by his home and chat a little bit about his life work on the zero-point energy. And so it's in that spirit that I want to have you join me as we drop in and have a candid discussion with a dear friend, Barry Setterfield. Barry, nice to be with you again.
It is a joy to be with you.
I have to ask you, I keep running into this issue of a zero-point energy. I've heard it for a while. I get the impression on the one hand it seems real, and on the other hand it seems to be disregarded. So let's start this exploration. First of all, what is the zero-point energy? Step one.
Okay. The zero-point energy basically is electromagnetic energy which fills the vacuum. It's intrinsic to the whole fabric of space. It's intrinsic. It goes through everything in the universe, goes through you and me and so on.
Well, why is it called the zero-point energy?
Okay. Let me put it this way, Chuck. If you take a perfectly sealable flask and pump out all solids, liquids and gases out of it, you would think you had a vacuum, a good vacuum. That was the definition of a vacuum back in the 17th century.
Okay.
Okay. Then they discovered that, okay, that vacuum can contain temperature radiation.
Sure.
Or heat radiation. Okay. So you then cool your vacuum down to absolute zero of temperature, minus 273 degrees Celsius.
Okay.
Okay.
So that's the zero we're talking about.
That's the zero that we're
Gotcha.
talking about. And that is called a bare vacuum. Okay. Now, it was then discovered in the 20th century that that vacuum contains an incredible amount of energy. It's called the zero-point energy because it's there at absolute zero of temperature.
Okay.
Okay. And what it is, it's actually electromagnetic waves of all wavelengths that are appearing there. And these wavelengths are distributed in an unusual fashion. There are very, very few long wavelengths, but the shorter the wavelength is, the more there are of them.
That would be, yeah, okay.
Okay. And so it means that at the atomic level, the zero-point energy is a seething mass of electromagnetic radiation and electromagnetic waves. And so it actually has a huge effect on atoms, but it has very little effect on larger scale objects.
Okay, what puzzles me is that what you've described to me, I think I understand, and yet I gather that there's a lack of reality to it in terms of modern physics. In other words, I run into physicists who tend to either dismiss or sideline or marginalize. They treat it as just some kind of academic idea rather than an actuality. So what's the history of it in terms of really discovering, is it real? And if so, what is its significance?
Okay, First of all, the zero-point energy was discovered as a result of an anomaly which science had come up against in the late 1800s, early 1900s. Theory and data were not agreeing in as far as radiation curves were concerned. They'd tried all sorts of ways to overcome this problem, and every method of overcoming the problem had failed. In 1901, Max Planck, overcame the problem in a very unusual way. He inserted another term in the equations, h, which became known as Planck's constant, later on. And by inserting h, this term, into the equations, he was able to overcome the difficulty. Now, this was a pure mathematical device. It was mathematics for the sake of mathematics, and it worked, and as a consequence it was accepted. But this puzzled Planck, because he was a practical man, and he realised that there had to be some physical reason behind this constant in there. And then after 10 years of working on this, he came to the conclusion that, okay, we can rewrite our paper. And he wrote what is called his second paper in 1911. It was published, in which there was a good physical reason for the Planck's constant to be there. It was a measure of the strength of the zero-point energy. And the zero-point energy was filling the whole vacuum. This concept was worked on by Einstein, Stern, Nernst, and others, and was proven to exist in the early 1920s.
In the 20s, okay.
Yeah. Now, you asked the reason why there's this idea that it may be real, it may not be real.
It seems to be marginalised in the minds of many physicists, yeah.
Yeah. Okay, there's a reason behind this. You see, in the 1920s, in the mid-1920s, 4 major papers were published on the basis of Planck's first mathematical exploration. Mathematics for the sake of mathematics. There was no physical reason. These papers had no physical reason for what was happening, but they used Planck's constant as a pure mathematical device to explain things and to explore possibilities. And this exploration led to what is now known as quantum electrodynamics, or QED physics. And
that's the general understanding even to this day, then?
That's the general understanding even to this day, and it's based on Planck's first paper, not his second one.
See, I leaned on that for a lot of our materials called Beyond Perception as I get into particle physics, trying to relate it to Genesis and the rest. So the point is that I leaned heavily on what I gather is the classical QED point of view.
Yes.
But you're telling me that there's another point of view under the covers emerging here.
Yes, indeed. In fact, up until 1925, when these 4 papers were published, there was a whole discussion going on about the zero-point energy and its effects on physics and so on, and its effects on atoms. And it does affect atoms because the zero-point energy has a large number of waves of all wavelengths, but the smaller the wavelengths, the more there are of them, so that by the time you get down to atomic size, you have a seething sea of activity of these zero-point waves. Anyway, what happened was that quantum physics developed using Planck's first paper, and in the development of this, all you had was a theoretical idea, a virtual idea for the zero-point energy. It wasn't a real construct, it was only a virtual construct, and this led to infinities and zeros in your equations. By the time 1962 came around, quantum physics had very, very well developed. But Louis de Broglie, who had published one of those 4 papers back in the 1920s, he had second thoughts about things. He looked back at what had happened. He said, I think physics has missed a key point here.
It takes a lot of guts for a guy to shift gears like that, isn't it?
It does. I must hand him full credit on this. And as a consequence of his exploration, Louis de Broglie said, okay, we should be looking at a real zero-point energy and classical physics in order to explain quantum phenomena. And this suggestion was taken up by a number of folk, and papers were published shortly after that In fact, there are a number of papers paralleling the 4 papers which were published in the 1920s, which set quantum electrodynamics on its path. And these papers published in the 1960s to 1980s and later, these established stochastic electrodynamics, SED physics, as a result. And the word stochastic means random. And you'll get coming at this from the random waves of the 0-point energy. They're coming in all directions simultaneously and in random. And what is happening is that an electron or any subatomic particle is being battered by these random waves of the ZPE. And as a consequence of this random battering, the particle is moving around, it's jittering around like this, so you have uncertainty in its position and in its momentum and in its orbit, because an electron, for example, is being hit something like 10 to the 20th times per second by these battering waves of the ZPE, and in one orbit around the nucleus, an electron will be battered 18,700 times just in one transit of its orbit.
So this is really what lies behind what we call the Heisenberg uncertainty principle, isn't it?
There's a physical reason behind it.
So many people take that and misapply it, but that's neither here nor there. The point is that's the dynamic
Yes.
that leads to the physical implication.
Yes.
And so now, what is there are a number of aspects to QED that lead you to some very bizarre, not counterintuitive kind of conclusions. Are these modified by the SED?
Okay, well, for a start, you have the randomness of position. The random battering gives you uncertainty in the position and the momentum of your subatomic particles. And there is a physical reason behind everything which happens in your quantum world. And this physical reason is, in fact, the 0-point energy. And as you have a look at, there are whole papers have been published about this, and it would take a long time to go and explain them all. But the point is that there is now we have a physical reason behind it, instead of just a theoretical concept.
Okay. Does the SED impact our concepts of locality and non-locality?
Yes, it does. The idea that we have here in SED physics is that you have a real particle. It is in a real position, but you have a real 0-point energy which is changing its location, and as a consequence of this, you can account for a whole host of physical phenomena.
I guess one of the questions I'm asking, what's the status of SED in physics today? Is it starting to get traction? Is it starting to see, because I would gather this is the kind of discussion that's relatively rare. I don't, people just have embraced the QED as you pick up journals and Scientific American, whatever, they deal in those terms. Is the SED starting to get, broader traction in
Yes.
the professional movement?
In fact, it is answering a whole host of questions that we've had that have never been satisfactorily answered before. SED physics, in fact, even though it's still a minority position, it is gaining increasing attention. And what you must realise, Chuck, is of course that QED physics had a 60 or 70 year head start on us.
Sure.
And so this QED has developed far more fully than SED physics has, but SED physics is overhauling things fairly fast in terms of explanations for phenomena.
We may be witnessing then some overturning or some major changes coming along in outlook, aren't we?
I see some major changes in outlook because what we have in quantum physics is a strange behaviour, a strange inherent property of matter, whereas in SED physics it says no, matter is being perfectly normal, it's just being battered by these impacting waves of the ZPE. So you can account for the de Broglie waves of electrons, for example. You can account for a whole host of phenomena here, just using SED physics rather than QED physics.
Now, can you discuss a little bit how that Planck's constant and the speed of light, how is that tied into these discussions?
Okay, this comes in from the origin of the ZPE. You know, when you take a rubber band and stretch it so you can hit the person over on the other side of the room or whatever. Okay, you're putting energy into the fabric of the rubber band. Okay. When you inflate a balloon, you're putting energy into the fabric of the balloon. And when you release the rubber band, it moves fast to start with and then slows down. Your potential energy of the stretching has been changed into the kinetic energy of motion. Same thing with the balloon. What happens is that when you stretch your rubber band, you're putting energy into its fabric. When the heavens were stretched as a result of the Big Bang, if you like, or as it says in the scripture, God created the heavens and stretched them out. We're told this 12 times in the Bible. Okay, so you have this stretching of the heavens. When you stretch the fabric of space, you're putting energy into the fabric of space. And this energy goes in as potential energy and then eventually changes to become the kinetic energy of the ZPE, of the zero-point energy. And this process takes a little time. It doesn't happen instantaneously. You know, when you have a kid on a swing, for example, you lift the swing way back, goes to a high point. That's all. The energy is all potential. You let the swing go, it moves down, and then at the bottom of its swing, it's moving at its maximum speed. It doesn't happen instantaneously. It takes time. Again, if you put some cold food into a hot oven, it doesn't get to the oven's temperature instantaneously. It takes a while to build up. So in exactly the same way, the ZPE took a while to build up. So, and if the expansion went on, the ZPE was still being built up. So what has happened is that the ZPE has increased with time. Now, if Planck's constant is a measure of the strength of the ZPE, Planck's constant will also increase with time. And this is what we found from our experimental data. We actually have the curve showing that Planck's constant has increased with time. But consider this. You have the vacuum has a greater intrinsic energy as a result of this build-up of the ZPE. And with this greater intrinsic energy, it means that atomic processes are slowing down, and it also means that the speed of light is slowing down. Two things are happening at the same time here. There's a reason for that. Let me see if I can get this concept across to you, Chuck. You know, when you go down to the ocean, and you see a speedboat go past on the ocean waves, where the two waves meet, they crest and peak, and you have white caps forming, like a concentration of energy. Okay. Where you have the ZPE waves meeting and they crest and peak, you have a concentration of energy forming there. Now, on Einstein's famous equation, E equals mc squared, he's showing you that energy and matter are interconvertible. And at these points where you have the ZPE strength being at its maximum, you find that there can be brought into existence, for a fraction of a second, virtual particle pairs. These are positive and negative electrons, positive and negative protons, positive and negative pions. There you have your positive and your negative forms, so that space is electrically neutral. Okay. These particles exist for a fraction of a second, then they annihilate, and it goes back into energy again. What happens is that as the ZPE strength increases, the number of virtual particle pairs in any given volume also increases. Today, at the strength that we have of the ZPE today, there are something like 10 to the 63 virtual particle pairs in a cubic metre. So in every cubic metre, there's, at any instant, there is 10 to the 63 of these virtual particles manifest. Now what happens is that a photon of light comes through the vacuum. It strikes a virtual particle pair, it's absorbed, and then a moment later the particle pair annihilates, the photon is emitted and goes on its way, but then it strikes another virtual particle pair. It's absorbed, the particle pair annihilates, and the photon is re-emitted. So the path of a light photon is rather like a runner going over hurdles. It takes a while for the runner to get from the start to the finish. If there were no hurdles, he'd get there in a certain time. The more hurdles you place there, the longer it's going to take him to get to his destination. And as the ZPE strength is increased, more virtual particle pairs per unit volume, the speed of light has decreased. Speed of light has taken.
So as the ZPE increases, the speed of light slows down.
Yes, and Planck's constant increases.
That's the key thing. In other words, the product of the two, speed of light and Planck's constant,
Is an absolute constant.
is an absolute constant.
Yeah,
Okay.
yeah.
And now what has happened to the ZPE during history? It, you say, is at speed now. What has it been?
Earlier in the earlier days of our universe, it was significantly lower, and
Lower.
it was significantly lower. This has a number of consequences. When the ZPE was lower, it meant the speed of light was higher. Atomic clocks also ticked faster, because the time it takes an electron to get once around in its orbit is determined by the number of impacts that it has by the ZPE waves and the number of virtual particle pairs it has to negotiate. And so one form of atomic clock is the time it takes an electron to get around once in its orbit. This is one form. There are a number of other forms, but they all basically behave the same way. So that as the ZPE strength increased, atomic processes slowed down. So the atomic clock was ticking faster when the ZPE was lower. And so the way in which scientists measure time today usually is by atomic processes, by the atomic clock. We're told in Genesis 1:14 that the sun, moon, stars are to be for signs, for seasons, for days and for years. And as you have a look at the whole business with the ZPE, it turns out that our orbital time, the time it takes the Earth to go once around the sun, this is unaffected by any changes in the ZPE. But the atomic clock ticked much faster when the ZPE was lower. And as a consequence, when the speed of light was, say, 10 times its current speed, the atomic clock ticked off 10 years in one ordinary year. And light travelled 10 light years in one ordinary year.
So the previous high speed of light would in fact impact our whole ancient history, wouldn't it?
It does. It allows, as you have a look at the curve for the ZPE, which we can come to in just a moment, when you have a look at the curve for the ZPE, you find that at the beginnings of the universe, it was over 10 million the speed of light was over 10 million times its current speed, and the atomic clock was ticking over 10 million times its current rate. So it ticked off, the atomic clock ticked off 10 million years in one of our ordinary years, and the speed of light travelled 10 million light years.
So that has the effect of collapsing our history. The history seems longer to us than it actually was, as you're saying.
Yeah, the history in science, the age of the universe is impacted by this, and you've got to reconsider the whole age of the universe, and the age of the rocks, the planets, the fossils, the stars. These are all measured on the atomic clock, and this was ticking faster back in the past. So these ages need to be corrected, and the way to correct them is we have data on the speed of light and atomic clock processes back to about 300 years ago, 350 years ago. In fact, we can go back a bit further with some radiometric data, which takes us back about 3,000 years ago. But the thing is that here's another effect of the zero-point energy. They discovered in 1987, one of these SED physicists made an amazing discovery. He discovered that, okay, first of all, there was a problem. The problem was that according to classical electrodynamics, an electron travelling in a circular orbit or travelling in any orbit around a nucleus would be radiating energy. It had angular acceleration, and this acceleration meant that energy would be emitted. And so as a consequence, you would expect on classical electrodynamics for an electron to radiate energy and spiral into the nucleus of the atom, and the whole thing disappear in a flash of light. Well, it doesn't happen. We're here, the disk is here, you and I are here, the electrons are in quite stable orbits. And when you ask a QED physicist why this doesn't happen, he says, well, because of Planck's quantum laws and the Heisenberg uncertainty principle. They go back to laws instead of a physical reason why it isn't happening.
Metaphors reign where mysteries reside. we don't understand it. We give it a nice label and then go on, right?
Exactly.
Yeah.
Well, what happened was that Hal Puthoff, back in 1987, he said, okay, let's accept that classical electrodynamics is correct and an electron is in fact radiating energy as it goes around its orbit. He said, let's also accept that the ZPE is in effect there. They calculated the energy lost by the electron, they calculated the energy the electron gained from the ZPE, and in a stable orbit the energy of the electron lost was equal to the energy that the electron gained.
Mm-hmm.
And so this whole stability of atoms is determined by this. In fact, Hal Puthoff made a conclusion at the end of his paper. He said, without the ZPE, every atom in the universe would undergo instantaneous collapse. Now, that in itself is very important. However, the point that I'm coming to is this, that the electron is maintained in its orbit in a similar way to what you have a lump of wood on the end of a piece of rope as you whirl it around your head. Your rope, the energy that you're putting into that rope is whirling the wood because you're supplying angular momentum. The ZPE is supplying angular momentum to the electron and maintaining it in its orbit in a very similar way. Now, if the ZPE strength is increasing with time, electron orbits are also increasing their energy. Okay.
Okay.
When an electron drops from an outer orbit to an inner orbit, it emits a photon of light of a certain energy. When the ZPE is stronger, as we come forward into the present, if the electron orbit has more energy, it is emitting more energetic photons of light. And more energetic photons are those photons which have bluer light. So as we look back into the past, we're looking back in time, we're looking back at galaxies more and more distant from us. And the light photons that we're getting from there are redder, systematically redder the further out we go. This is called the redshift. And we can measure the redshift. As a consequence of this measurement, we can say what the speed of light was, what the ZPE strength was back then, and consequently we know what the speed of light was and the rate of ticking of the atomic clock.
So the red shift is really due to a broad structural change, not the Doppler effect.
Not the Doppler effect at all. In fact, the Doppler effect has been disproven on a number of occasions. And first of all, you find that the redshift is in fact quantized. It goes in jumps, and some of these quantized jumps go right through the center of some galaxies. Mm-hmm. If the redshift was due to motion, it would mean that the galaxies were shearing apart, but this isn't happening.
So the Doppler effect was the basis of Hubble's law, for which the satellite's name, the
Yes.
telescope's name.
Yes.
But that really is, in a sense, an error of history.
Yes, an error of history, although you've got to realise this, that Hubble himself was very cautious about making that application. He was very cautious about saying it is in fact a Doppler effect.
But still, that's what he's named after. And,
yes.
But the Doppler effect is still taught in school, and it's wrong, isn't it?
It's absolutely wrong.
It's one, I make a list of these things. There's so many things in science that our kids are taught that are just not true. And we don't go back and correct the textbooks or the perceptions. And that's what gives us impediments, because my premise is the more you know about real science, the true science, the more you see the more comfortable the Bible reads. That's been my orientation. But okay, now if the ZPE going back in history, it was
lower back in the
lower
past.
back there. What's the impact of that on organisms of animals and that sort of thing? Can you talk to that then?
Yeah, okay. It does have a surprising consequence here, because as you have a look at what the ZPE does to the vacuum itself, you find that it affects the electric and magnetic properties of the vacuum.
Okay.
Okay. So what happens is that as a result of this change, electric currents were stronger when the ZPE was lower, voltages were greater, and currents move faster.
Okay.
Okay. Now, as you have a look at a human being, or as you have a look at animals like dinosaurs or whatever, you find that all of us are behaving through the result of the transmission of nerve impulses. The transmission of nerve impulses is basically by an electric current. When the ZPE was lower, the currents moved faster, and this allowed you to have a much shorter reaction time. As a consequence of this, you could grow into a larger size and still be an efficient being. So for example, today a dinosaur like Diplodocus, it would take about 40 seconds to get a message from his tail to his brain. Okay, and another 40 seconds to get a message from his brain back to his tail. The beast would be totally unfunctional. He couldn't work as an efficient beast at all. However, back in those days, back in the days when the dinosaurs were there, it turns out that the ZPE was so low that you could get a message from his tail to his brain and back again in less than 1/10 of a second. So he would be a very efficient beast. So as the ZPE strength built up, the speed at which the nerve impulses were transmitted slowed down, and it was only the smaller varieties which survived.
I understand what you're saying, but let me follow it a little more carefully. So if the ZPE is lower, the speed of light is faster.
Yes.
Electric circuits go faster,
Yes.
in effect.
Yes.
Okay, see that's the thing, that as a ZPE is lower, there's
less resistance
less
to
resistance.
Yes.
Okay, so that could be a major factor in the fact that not only dinosaurs, but certain kinds of plants and so forth grew larger back there, right?
Mm-hmm. Yes, so for
Okay.
example, in the Adelaide Museum near where I used to live, you walk in the door there and there was a massive scorpion, a Eurypterid, which was 8.5 feet long. Incredible. Today scorpions only grow about 9 or 10 inches. This is fortunately, yeah, but due to the a stronger ZPE, the nerve impulses can't make that a more efficient beast. It wouldn't be efficient if it was any longer than 8 or 9 inches.
This is what's so fascinating for us to also, it affects our worldview to realize how much of history and the components of history are impacted by the ambient conditions, ZPE being but one of them. Mm-hmm. And the whole thing is an interactive design.
Yes.
The environment and the things in the environment are highly skillfully orchestrated. That's what's so staggering. So, but anyways, as the ZPE starts to increase, things get to the size that we're used to.
Yes.
That's what you're saying.
Yes.
Okay.
There's a decrease in the size of a viable functional organism.
And we get a grasp of the ZPE by looking back through time, by looking at distant galaxies.
Yes.
And getting from them a measure of the ZPE
Strength.
back there.
Yes, that's right.
And that gives us a way to calibrate what was going on in the universe.
Yes.
Wow. So the whole idea of grasping not only the ZPE, but the whole stochastic electrodynamics is crucial in building a valid worldview, isn't it? That's one of the challenges we all have in our culture, is to help our young people build a worldview that's valid, rather than inculcate them with a worldview built on things we know are not true. Mm-hmm. And that's what really bothers me, because so much of what we teach our kids are things that scientists, true scientists, really know are incorrect. I usually use the Nebular hypothesis in astronomy as an example. Mm-hmm. Still taught in college. Mm-hmm. And yet anyone that does the math realizes it's not a viable, even Laplace, back when Swedenborg first proposed it, had the math background and hurt us all by not applying his knowledge to demonstrate it wasn't mathematically tenable. But as it gets accepted, then it gets inculcated in the culture, and now no one questions, but it's mathematically untenable, as is what we call the theory of evolution. Yes. Which when we say that term, we really mean biogenesis, and it clearly is assaulted by virtually all the facts. Yes. There's no way mathematically And that's, Hugh Ross has done a good job, I think, in promoting the whole, what we call the Anthropic Principle. Over 400 measures that if any one of them change one part in a million, life's impossible. Well, that's just a very elegant definition that life is a miracle.
Yes.
And yet we don't teach that in school.
A couple of points that I'd like to pick you up on there, Chuck.
Okay.
First of all, as far as the Anthropic Principle is concerned, okay, people look at this and say, okay, if the speed of light changed, everything would be so different that life wouldn't be, you wouldn't be able to live your life or anything. Okay, the one thing which has happened in all of this, in all of these ZPE changes, is that energy has been conserved in your atomic systems. So, for example, Planck's constant times the speed of light is an absolute constant. Energy is conserved. You find that E equals mc squared. As C was higher in the past, M was lower, so that energy E in that equation was conserved. And so, as you study the ZPE position and the SED position, you find that energy is conserved with an increasing ZPE, and therefore the application of the Anthropic Principle is again validated, but on a slightly different basis.
Oh yeah, but I understand the basis. That leads us right into another discussion. That's about the fine structure constant. We run into that, if you do some reading in this area, you run into that, and to the layman, it's not clear what they mean by that, and that may deserve a little illumination in terms of the ZPE and the rest too.
Yeah.
What is the fine structure constant, and how does it impact this?
Okay. Originally, the fine structure constant was defined as the ratio between the speed of light and the rate at which the electron travelled once around in the Bohr orbit, in the first Bohr orbit.
Okay.
So that if the speed of light was higher, it meant that the electron was travelling around in that orbit much faster.
Okay.
Okay, that ratio is a constant. Now, as the way we have defined it today, the fine structure constant is made up of two sets of two constants each. One is Planck's constant times the speed of light, hc, which we've already referred to. The other is the electric charge on the charge on the electron and the permittivity of free space.
Permittivity. Okay.
Yeah. Okay. So E squared over epsilon is also a constant, and as it turns out, therefore, the amalgamation of all of those four constants again gives you an absolute constant. Now here's a problem. They have tried to show that the speed of light has actually changed by examining the fine structure constant. When you have a look at the formation of the fine structure constant using these four other atomic constants, you cannot find any change in the speed of light because there has been, if you like, a conspiracy between the constants, so that there's inverse change. It says H goes up, C goes down, so that HC remains an absolute constant.
That product between those two are
Yes.
constant.
Yes, and so in a similar way, you find for the other two constants in the fine structure constant, the same thing happens. And so as a consequence, the fine structure constant you do not expect to vary as an entire entity. However, the parts making it up will vary individually, but in an inverse relationship with each other.
I see what you're saying.
And so it has been a mistake by some to say that, okay, because the fine structure constant hasn't shown very much change, we don't think the speed of light has changed. That isn't what the data show. The data for the speed of light itself on its own does show a considerable change. But if you just look at the fine structure constant, you have this in conjunction with other atomic constants which have been changing inversely, so that any ultimate change of the whole thing is negated.
But if the speed of light is changing, then Planck's constants will be changing proportionally.
Proportionally, yes.
Gotcha.
Yes.
Okay.
Now, there's one other point that I'd like to catch up on with you as well. You're talking about the formation of stars and galaxies and planets by the Nebular hypothesis and so on. There's been another development in astronomy just recently, and this is in the area of plasma physics. And by plasma, I'm talking about the fourth state of matter. You have solids, liquids, gas. Then if you heat the gas to high enough temperature, it strips the electrons off and leaves you with ions and electrons, positive ions, negative electrons. This is a plasma. And if you have an ion moving in one direction or an electron moving in the other direction, this is an electric current. So plasma physics involves the ZPE. What is happening with the ZPE? As the ZPE increases in time, you have electric currents slowing down. So back in the past, when the ZPE was very, very low, you have your plasma physics allowing you to have very strong electric currents moving very, very quickly and strong magnetic fields. Now we know already from physics, from the physics that we've already established, that plasma effects and electric and magnetic effects out in space are something like 10 to the 39 times stronger than gravity.
Okay.
And this
Yeah, I'm
makes...
very familiar with that because I published some briefing packages I called the one beyond Newton, meaning that the astronomers have never really, generally haven't discovered the Maxwell equations. In other words, the real reality outside the solar system itself, you start getting those great distances, gravity becomes negligible, and the really electrical issues. And we've developed that pretty well, but we did all of that without really a perception and understanding of ZPE. So that's the dimension here that is refreshing and provocative. So go ahead, I didn't mean to stop you there.
No, that's fine. And what has happened then, Chuck, is that in the laboratory, we can see the interaction of plasma and electric currents in Birkeland currents in filaments and so on. And you can see how they form galaxies. In fact, we get miniature galaxies formed in the laboratory. We can measure the rate at which this happens. We can measure the rate at which these things pinch to form.
Which is very quick, isn't it?
Very quick in the laboratory. We're talking of minutes and seconds. But what happens, you then upscale that to outer space, and then you realise how long it would take out in outer space at today's ZPE. But then when you factor in the change in the ZPE into that, it turns out that you can get your plasma interactions happening in such a way that you can form a whole universe in 6 literal days of 24 hours each.
Wow. Now that's a staggering declaration. The entire universe demonstrably coming into existence in 6 24-hour days. That assertion is so exciting, we should throw that out there as a challenge. And the ZPE story defends that perspective. So that really is a major, major trump card for what we classically call the young earthers. In other words, the idea that the universe has a much younger history than we've realized.
Yes.
Because we failed to really understand and apply, of all things, the zero-point energy.
Okay, so this is dependent upon 2 developments. One is the development of the zero-point energy, which an understanding of that, which has happened since 1962. And the second one is the development of plasma physics, which has only happened since 1992. Mm-hmm. And as a result of these 2 things combined together, we have a very valid reason to believe that the scripture is in fact correct.
So now our challenge really is to get people to examine and repair their physics illiteracy about the ZPE and the SED and of course the plasma physics that surround what we used to call astronomy, mm-hmm. but is much a bigger subject these days. Yes. So that's exciting stuff, and it's exciting for me because I'm fully aware of the fact you've devoted your whole life to really exploring ZPE and its derivative implications, and so I want to encourage you to continue the website and continue the publications, and I'll look forward to being back here.
So thank you very much, Chuck. It's really been a joy to catch up with you again,
okay.
And I hope that this has given you a deeper understanding.
Oh, very much so. I really appreciate the understanding, and from the moment that your tome, your life's work landed on my desk, I knew I was overdue to get back here and to get refocused on the zero-point energy is vastly more significant than I had any grasp before.